Hello everyone, we are excited to present our work, Long-Tail Internet Photo Reconstruction. In this research, we introduce a paradigm for training 3D foundation models that generalize beyond densely captured imagery. Let's start by revisiting the fundamental problem. Real-world internet photo datasets, such as megascenes, exhibit an extreme long-tailed distribution. At the head of this distribution, we have a few famous landmarks that are densely photographed and relatively easy to reconstruct. However, the vast majority of scenes fall into the long tail. These sites contain only sparse, noisy, and unevenly distributed imagery. Under these conditions, classical reconstruction methods like CoalMap frequently fail. Modern feed-forward models like VGGT learn powerful priors from millions of images. Yet because they are trained on clean, dense, evenly sampled captures, they often fail to recover consistent geometry on the sparse and uneven imagery of long-tail internet scenes. Therefore, our primary goal is to train more general 3D foundation models that can robustly handle the long tail of noisy, sparse, and incomplete internet photo collections. To achieve this goal, we made two major efforts. First, we addressed the data shortage by curating the MegaDepthX dataset, which provides clean, large-scale 3D supervision. Second, since real long-tail data lacks reliable ground truth, we address the training distribution gap by proposing a novel sparsity-aware sampling strategy. This allows us to simulate difficult long-tail image sets during training and evaluation. Let's first discuss the MegaDepthX dataset. Learning 3D reconstruction priors from internet photos requires high-quality 3D supervision, and that supervision is only reliable when scenes are densely photographed. So we build our dataset on densely photographed scenes where we can actually trust the reconstruction. But even on head scenes, CoalMap often struggles. We therefore adopt a stronger pipeline, combining master SFM with doppelgangers++. It handles challenging viewpoint distributions and ambiguous viewpoints more reliably than CoalMap. Beyond SFM reconstruction, we implement rigorous data filtering. We manually verify the reconstructed scenes against external references, such as Google Earth, discarding any geometry that is degraded by non-static human, inconsistent objects, or doppelganger ambiguities. Through the data preparation, we finalize the MegaDepthX dataset. It contains 1,865 accurately reconstructed scenes. This is 7 times the scale of the commonly used MegaDepth dataset, providing us with the massive, clean supervision required for our next step. Having established the dataset, we encounter a fundamental problem. Reliable ground truth supervision is practically non-existent in true long-tail scenes, making direct training in this regime impossible. We bypass this problem by sampling sparse views from the SFM reconstructions in the MegaDepthX dataset to simulate long-tail scenes. So before simulating the long tail, we first looked at what makes it different. 2 things stood out. First, the view graphs are really sparsely connected. About 8% of cameras link to only 2 or fewer others. Second, the overlap between images is weak, far fewer feature matches than in head scenes. So the long tail isn't really about having fewer images. It's about viewpoints that are fragmented and barely connected to each other. Based on these properties, we designed our sparsity-aware sampling strategy. Our algorithm simultaneously satisfies 3 objectives. First, it must span diverse visual perspectives. Second, it must maintain sparse overlap to emulate wide baseline conditions. Third, it must still preserve sufficient local co-visibility so the geometry remains reconstructible. The algorithm operates in 3 steps. First, for viewpoint diversity, we identify the viewpoint clusters in each scene via community detection on the view graph. Next, to preserve overall scene connectivity while maintaining sparsity within limited nodes, we construct a minimal structure linking all identified communities by an approximate Steiner tree algorithm. We then perform greedy sampling to select a diverse subset, balancing broad spatial coverage with sufficient co-visibility. Here we show one example of this greedy sampling procedure. For more details about the sampling algorithm, please refer to our paper. Let's now look at the experimental results. Quantitatively, we observe that our fine-tuned model significantly improves pose and geometry accuracy on emulated long-tail evaluation dataset when compared to the pre-trained models. Qualitatively, our fine-tuned model produces more accurate camera poses and much denser, more consistent 3D point maps compared to the pre-trained baseline, especially on sparse and hard scenes. It generalizes well across varying camera intrinsics and challenging appearance changes. Thank you for watching. For more information about the dataset, the code, and additional results, please visit our project page.